and you're ready to go. Have a good session.
Well, thank you very much. Hello, everyone. Good morning, afternoon, evening, middle of the night. It is our pleasure to announce and introduce our second invited speaker, Robert Watson. Robert is a reader at the University of Cambridge, and he's doing research at this intersection between hardware and software to, well, improve the security of systems. He's on the board of directors of the FreeBSD Foundation and has been actively contributing to FreeBSD. He's been working for some time in industry research labs and, well, is now in academia. The reason that we invited him is that for over 10 years, he is now leading a research effort into Cherry, security enhancement to existing computer architectures that, well, I'm sure we're going to hear a lot more about in this invited talk. So thank you very much for agreeing to speak here, Robert, and the floor is yours.
Great. Thank you very much. I'm very pleased to be here to talk to you. I will commit that act of sharing my slides. Right, I say good morning. No idea where most people are. It's probably not morning, but good morning anyway. And thank you for the invitation to talk to you today. I'm going to be talking about Cherry, or Cherry to Morello, a long-standing research project here at the University of Cambridge in collaboration with SRI and now also ARM, Google, Microsoft, and many others. I should start by acknowledging my co-investigators, Simon Moore, Peter Saul, and Peter Neumann, as well as a large host of contributors over the years, some for as many as 10 years. Could not have done the project without such a great set of collaborators. We are working from low-level hardware up through the operating system to the applications. But the center of our work is really computer architecture, this interface between hardware and software. It started out as a set of experiments. If you perturb that interface and you chase the changes up into the software implementation, down into the microarchitecture, you validate the ideas and you iterate on them until they become viable and helpful and useful and ideally good performing, low power, all those nice things on both sides of that interface, then you've accomplished something, you've met your goal. So I'll talk to you about this for the next sort of 45 minutes or so. So I'm going to introduce the idea of capabilities in the Cherry architecture, talk to you a little bit about our ongoing research. If you want to learn more about this, you should go to our website and see our numerous papers and reports and presentations and various other things. Perhaps most importantly, though, you can download emulators, you can run with our adaptive software stack. And you should know that you'll be able to get hardware that does this stuff from ARM starting next year. It is not mass production hardware, it's experimental hardware, but it is a high performance processor design that I'll talk about a little bit later in my talk. So also know, of course, we have written a lot about the topic. If you just want an introduction to the work, our introduction to Cherry technical report is not a bad starting point. If you need maybe some heavier reading before bedtime, we have a very long, many hundreds of page instruction set architecture, sort of design reference, microarchitectural information, and so on, and various other guides. Another important thing to tell you, though, is that Cherry is open. It's a set of open ideas that we've created in the hopes of influencing technology, but with the idea that everyone can use it. The goal is to improve computer security. So all of the intellectual property I describe is, if it's in software, it's open source. We have not protected the ideas and patents and so on, and don't intend to. So what is a capability system? A capability system is a design pattern. It's an idea about how we control access to resources, and we can impose that design pattern on a lot of different substrates or execution platforms. It can be processors, programming languages, operating systems. What is a capability? It's in the abstract, it's the communicable, unforgeable token of authority. It's a thing you hold that allows you to do stuff. And if you don't hold the thing, you can't do the stuff. In capability-based systems, resources are only reachable via capabilities. We define the idea of capabilities in non-capability-based systems. They're useful, they're helpful. Things like file handles and so on in Unix resemble or are very close to capabilities. But a key aspect of the design of a capability system is that there is no way to access things without a valid capability derived in some valid way. And why do we do this? The goal of a capability system is to limit the scope and spread of damage from accidental or later, sort of come the 1990s, intentional software misbehavior. And the way that we do this is to make it natural and efficient to implement certain ideas in software. And there are really two principal design concepts here. The first of these is extremely well known. It was written about in the 1970s at MIT, at Cambridge, and elsewhere, around the time of the inception of these ideas. That's the principle of least privilege. It says that if you run software with as little privilege as possible, then when it's compromised, when it suffers a fault, the scope of the damage it can perform is greatly potentially limited, depending on how narrow you limit those privileges. The second principle, I think, existed in these early systems, but was not explicit in their design goals. And it's one we've really pushed on. It's the principle of intentional use, or so we call it. This says that when you have a set of software privileges, even after you've minimized them, it could be quite a large set, it is really important to explicitly select the right privilege to use. And we see a host of attacks that have to do with, they're successful because there's too much privilege, but we also see attacks who inherent in their design is the fact that, yes, you were supposed to be able to hold that privilege, but you used it for the wrong thing, which is really important. Sometimes we see, an aspect of this idea come out in the notion of the confused deputy, often talked about by capability system designers. So if that's the set of ideas, what is Cherry? Cherry is an architectural protection model. It means it's an abstract model. We can apply it to many different architectures. It composes the concept of the capability system model with hardware and software. It adds new primitives to the instruction set, to this architecture I was talking about a few minutes ago. We build those ideas into the microarchitecture, and we enable new kinds of security behavior in software. The goal of Cherry is to mitigate vulnerabilities in C and C++ trusted computing bases. These are the hypervisors, the operating systems, the language runtimes, often the web browsers that we use. It's not that we don't think high-level language is important. You should absolutely implement your system using a high-level language. It's just we notice that you don't implement your system using high-level language, at least not if it's a mass market mainstream system used all over the world. And it's really hard to switch to those languages. And even when you do, often you discover the language runtime is still written in C or C++. So there is an interesting problem to solve. Maybe the problem of solving will go away. I hope so. Maybe software will become largely formally verified and you won't need all kinds of dynamic enforcement. But I think in the meantime, you may need Cherry. There are really two things we do to mitigate vulnerabilities. They both revolve around this idea of capabilities. And it's interesting that you can do both of them. So the first of these is fine-grained memory protection. This is about deterministically closing many kinds of arbitrary code execution attacks. And then where we can't necessarily close the vulnerability itself, we can sometimes impede the exploit chain tools that people use to escalate privilege. The second concept is scalable software compartmentalization. This is about mitigating vulnerabilities that exist in higher level software. The accidental, maybe intentional, but miscrafted intentional use of arbitrary code execution in language runtimes or script interpreters, or maybe in preventing the accidental overwriting of the wrong files in the file system. So the principle of least privilege and the principle of intentional design correspond to both of these. They support both of these goals. So we primarily right now work in the RISC-V architecture. Cherry RISC-V is our research architecture. We work on FPGA prototypes. But also, as I mentioned at the start of the talk, ARM is producing a processor, a system on chip, and a board called Morello. Morello, for those who don't know, a kind of Cherry. This is an industrial scale and industrial quality demonstrator of the concepts to try and validate them. In some sense, the first stage of validation has happened. They've been able to build it. It's microarchitecturally viable. It will be a high performance design. But I think then there's a large set of experiments we run on top of it to try and demonstrate that these ideas are, we hope, good ideas, that they can have the impact that we desire on the way to transitioning to a more structured product. So thinking about this stack, at the bottom of it, we have microarchitecture. In the middle, we have this instruction set architecture. And then we have a set of components up and down the software stack that are able to use the hardware. Sometimes people draw system software above compilers, below compilers. We compile our system software with compilers, so we kind of consider that to be at the bottom of the stack. So Cherry capabilities are an architectural primitive. They're something that's visible as a data type in the architecture, and they then support and are used by, in our environment, the whole of the compilers of the system software, maybe the runtime linker, applications themselves. The programmers, they use capabilities implicitly, but they don't think of them as a primitive they're programming with daily most of the time. In fact, for many uses, the capabilities are effectively transparent. And for the end user, the goal is that this should all be invisible. What do capabilities do? Well, they allow those pieces of software to control and manage their future execution. They restrict what a program can do in the future and the way that it can represent it. So often we have a piece of trustworthy software, potentially trustworthy software, interacting with untrustworthy behavior on the internet, right? We want to know that the application can constrain its own future behavior, but it's not limited to that. We can also start arbitrary binaries we download off the internet and constrain their behavior. The microarchitecture is going to implement these capabilities and also some tagged memory for us. It's going to enforce these invariants On the manipulation and use of capabilities, something called guarded manipulation. So you can only manage capabilities in certain ways in hardware. And then we have a set of protection properties that push up and constrain this feature execution, invariance and safety properties. So let's talk about how we got to Cherry. So I told you it's an architectural mitigation technology for C and C+ TCP vulnerabilities, roughly speaking. But we have these new data types, this new tag memory. The thing I haven't told you is that an important design aspect, and really one of our key contributions, I think, is the clean composition with existing designs, contemporary designs, right? RISC architectures, the actual microarchitecture that exists in superscalar designs today. MMU-based operating systems use virtual memory, C and C++ software. We can run on, with, and be integrated with all of these things. Yes, there is some disruption. The goal of the project was to, find the most disruptive point that could possibly be adopted, but not a point slightly beyond that. We can't quite tell, I guess, at this point in the project whether we went across that tricky line. Right? I mean, it's been a successful research project. We've published papers, we've made prototypes, we have all that stuff, but we still can't quite tell if it's going to be successfully transitioned. But obviously, there are some good signs, and we hope that it will. And of course, new hardware enables new software development. Our goal is to support incremental software deployment. So we need to be able to have a story about how you run your existing software, even if maybe it's not as well protected as the newer software that you've recompiled or modified to use these features. Another interesting thing about our project, it's not just hardware-software co-design where you iterate across this interface. It's actually hardware-software semantics co-design. And concrete prototyping. So we have our abstract protection model that's going to be applied to different instruction set architectures. It didn't start out that way. It was a very sort of ground up, visceral experience, adding it to the MIPS instruction set and designing it as we went, learning about it. But then we realized we could abstract the idea away. Much the same way virtual memory can be abstracted away from memory management units. You can have portable software that uses virtual memory. So we've also applied it to RISC-V, where we now do our research, as I mentioned, to ARMv8A. We also have a initial budding sketch of an adaptation to the x86 architecture. So it is not so specific to RISC, despite the acronym. We then have a set of formal models, instruction set models that are described with formal semantics, about which we can do proof. And we do proof. We have a paper published, I guess, a year or two ago about our Cherry MIPS architecture. We have substantial in-progress work around RISC-V and Morello as well. We have emulators, we have multiple FPGA prototypes. The formal proofs about the ISA show us that these feature constraints hold no matter what instructions you run. Software is contained within compartments or has protection properties. We have a complete compiler suite, operating system stack, C and C++ languages, and then the open source application corpus. I'll mention that a little bit more later in the talk. And because it's co-design, you do it over and over again, but because we have semantic co-design involved, we're also able to improve the security properties, improve our ability to do proofs, run aspects of verification and proof and continuous integration, and so on. Really a key aspect of the approach, and you need it. One reason you need it is that Cherry is a very intricate approach. It's engaged in minute detail and the structure of instructions and the behavior of memory access. If you make mistakes anywhere in that, your design, are you going to get the security properties you want? Perhaps not. And so we need to know that the instruction set design is correct. Ideally, of course, as with all these kind of things, you push the proof down into hardware design, up into software design. We're not there yet. I mentioned a 10-year timeline. We had DARPA funding for the first 4 or 5 years to sort of develop the initial ideas, a set of transition contracts and grants. I mean, most recently, our work has been supported by UKRI, in particular in the UK, who've been supporting the development of the Morello processor. But I thought I would kind of highlight a few key moments. I mean, the first couple of years is really just building the platform to do the research. I remember in 2010, there was no RISC-V, there weren't open source cores in nearly the same quantity floating around. We had to build our own MIPS processor. We then spent several years trying to understand how do you hybridize these ideas. We started with a very simplistic atom smashing of the ideas about capabilities with the hardware design, and we began to build up the operating system. Moved on to compiler work, looking at efficiency, how should it affect OS design? And then most recently, looking at RISC-V, temporal safety, being concerned about speculative execution attacks, how they interact with our model. And through all of this, we're attempting to publish. The first paper is actually 4 years into the project, which is a long time for an academic project. But as a pretty good pipeline is built out across, various kinds of venues, whether it's hardware design or, security or languages and formal models and so on. And hopefully we'll have more to say in the future about this work. This is one of those days when PowerPoint, you press the button and then eventually the slide turns up. So what were our design goals and approaches? A key thing we wanted to do was deconflate memory virtualization and protection. So in hardware design, associative structures are particularly expensive. They're particularly challenging to work with. They use lots of power, and memory management units, which use them today, basically take your address and they look them up in these structures, and then they're able to find protected information. So they protect based on, roughly speaking, location in memory. We wanted to add complementary protections, but we did not want to add more indirection or more tables. We borrow existing references and indirection that happen, are present in code and data. We use pointers, right? We associate our protection state with them, and we protect them and the things that they point to. So it's a complementary design. If it looked the same as the MMU, it would have the same scalability properties or the same protection properties, with minor tweaks. We actually wanted a quite different kind of protection. Because we can use the existing pointers, we avoid adding indirection, we add in tables, adding associative structures. We're able to flow the information through the microarchitecture in a way that's relatively non-disruptive. It is an architectural mechanism that enforces software policies. So, what kinds of policies, where do they come from? Thinking back to my initial description, they're language-based properties, things about the structure and execution of your code, spatial, temporal memory safety, protection of the pointers themselves. We get that from compilation, linkage, operating system execution, the runtime environment, including the runtime linker. But then we also want this compartmentalization property. This is where we are potentially more disruptive to software. We don't require much change to your C language code or your C++ code. But if we want to have new kinds of software compartments, that has to somehow be expressed by the programmer. So here, maybe we can maybe reuse an existing concept like a process, but maybe we need new concepts associated with, objects or libraries or whatever it is we may choose to use. And here is the potential for greater disruption, but also maybe, greater gain. So I told you protect pointers. Well, the first thing, we sort of had to rediscover this, I guess, in coming up with these ideas. But pointers are derived largely from other pointers, right? You start off with a set of initial pointers that tell you where stuff is, where space is in memory, and from there you build different hierarchies used for different things, so control flow for data access and so on. So what we're going to do is we're going to reinforce that hierarchy to try and harden it down so that it can't be manipulated and attacked. And this serves the goal of memory protection, but also compartmentalization. So integrity and provenance validity. So you can't just inject them and make them up. You can't corrupt them. Provenance validity is slightly more complicated. It says that a valid pointer is derived from another valid pointer. It's only been manipulated in valid ways. And I'll talk about the valid ways. Bounds give us some spatial protection. They say, okay, this pointer has been narrowed down to a specific piece of memory, but we need to constrain how the bounds changed. So we have a monotonicity notion. This moves us, the left hand, it begins to sound a bit like fat pointers and things, right? As you move to the right, they sound more like capabilities. So monotonicity tells us you can't increase the bounds over time. And that's kind of interesting. So if you decrease the bounds on your pointer to describe a memory allocation and you pass it back to the memory allocator, there's the potential for some disruption there. I mean, the software isn't allowed to overflow buffer, which is great, but memory allocators often store the metadata just outside the buffer, which attackers think is wonderful, but the architecture is now going to prevent access to that metadata. So maybe there's some implications for software design that aren't just the same as bounds checking. And we have a permissions mechanism, a fairly sort of narrow set of permissions, because architecturally we don't do that many things with pointers, but it's still a useful thing to have. And as I said, we can build other things on top of this primitive, like spatial temporal memory protection, compartmentalization. I'd be remiss not to show you a capability, but I'll actually try not to spend too long on it because I want to talk to you more about the ideas. So a capability, roughly speaking, is an address, but we're going to add some stuff to the address. We can have tags that protect the values as they flow through registers in memory. If you try to access memory through an untagged, or at least a capability that has an invalid tag, we're going to throw an exception. And if you try to corrupt a capability in memory, or you try to transform it in a way that's not appropriate, then the tag disappears. So this tag tells us that a capability or a pointer is derived validly. It's in this tree of potentially valid pointer accesses. The bounds, we have to be fairly clever to fit them in still quite a large space. In the abstract, the bounds are 64-bit addresses, 2 of them. We compress them relative to the address itself. This is part of what makes this viable and practical. And then we have to support some strange behaviors. C people like to push the pointer outside the bounds with surprising frequency. So we have to allow that to happen, subject to some practical constraints. Permissions I mentioned, and we have some other features too. I won't go into detail on these, but they allow you to make pointers opaque, so you can use them in compartmentalization context to refer to objects you cannot yourself immediately access. You have to go through some non-monotonic transformation to reach them. And again, just like high level bit of the story, we extend the existing register file. We add on this capability metadata of these tags that has some consequences for the microarchitecture. It has consequences for dynamic performance that have to be thought about carefully. We extend the program counter. This gives us control flow protections. We have another sort of hidden set of, they're reserved registers, system registers. They allow you to both engage capabilities in the exception handling mechanism and also control legacy code that doesn't know about capabilities. The memory itself is extended with tags. Won't get to explore that much in this talk, but this is more complicated than you might think. I mean, if you're willing to remake all your DRAM sticks to add more bits, or maybe you can borrow ECC bits, then okay. But many systems, especially mobile systems, aren't equipped with those features. And so where are you going to store the tags instead? And then lots of thinking about low-level system mechanisms. What does it mean to throw an exception? Is that itself a domain transition? Yes, it is. I mentioned full modeling. I won't spend very much time on it. Just to say, Peter Sewell's group at Cambridge has a modeling language called Sail that converts into various other languages like Isabelle and Coq and so on. So his team and our team collaborated to develop the RISC-V model, now used by the RISC-V Foundation. We can then use that for a lot of different things. We can use it for, SMT solving. We can use it to actually generate the specification itself. If you look at our PDF, all the pseudocode in there comes, is included inline from the formal model. We can use it for compliance testing, for test generation, and we can of course use it to prove things, which is very important to us. Although actually, we did our ChariTest 5 implementations in software and hardware entirely by using generated tests, either in intelligent ways or less intelligent ways from the formal spec and checked against it as an oracle. And I said we have a paper from a couple of years ago on the work around an L3 base model, which was one of our earlier modeling languages. And we have actually recently completed the successful proofs around ARM's Morello architecture, which is something we're very excited about. Haven't written a lot about yet. I said it's hardware software co-design. That means we've done some work around the hardware. I'll talk to you very briefly about it. So we started, as I said, we developed our own, multi-stage pipelined MIPS core, worked with that very successfully for about 7 or 8 years. We've transitioned our research over to RISC-V, where we have 3 different microarchitectures, sort of microcontroller shaped, small pipeline processor, and then superscalar multi-core design. These use the BSV BlueSpec system Verilog, a higher level HDL, and then we run them primarily in FPGA, although also obviously in simulation. And this is a very effective tool suite. It allows us to understand the disruptions to microarchitecture at different scales with different kinds of processor designs, understand the dynamic performance, and so on. These are all open source designs, I should point out. We had to come up with some novel techniques. How do you squish the bounds down? Well, it turns out there's actually a literature in squishing bounds into small spaces. We found that literature didn't do what we needed. We needed some properties of C that were different. We needed some microarchitectural properties, so we published around that. I mentioned the tag memory implementation techniques. In particular, we have a set of techniques to store tags in your DRAM, but in a reserved chunk in a table. Making that access efficient and getting a suitable locality is really hard, required a lot of hard work and thinking about software behavior. We have QEMU simulator. That's primarily what's used by people working on software development. And actually, I should update that slide. We now have one for ARM Morello as well. And then there is the ARM Morello implementation, and we'll come back to that. Waiting PowerPoint deciding to go to the next slide for some reason. Proving remarkably unsuccessful. I may have to try quitting from the presentation and start just again in a moment. Hopefully that has just worked. So I thought I'd show you just a high-level picture of what happens to processor cores and memory subsystems. So in the processor core itself, we've added some new instructions and new operations to manipulate and manage capabilities. We have extended the exception model, although only modestly. We've extended some of the implied registers that exist, such as the program counter, added this default data capability that transforms non-capability relative accesses. These are legacy instructions from our perspective, that some people view not just as legacy, but important compatibility. Status registers. In the design we have in ChariTest 5 and in Morello, we've done it to merge the register files. Capabilities are extensions to general purpose registers. In our MIPS implementation, we actually didn't do that. We had a separate set of registers that were capability registers, more like floating point. And the two designs have upsides and downsides. And the design merging the register files is much more conservative in terms of control logic, and especially for smaller processor designs. So we found that worked well. It also helps a bit with ADI design. The memory subsystem has to carry around these tags associated, multiple per cache line. We transport them around in our microarchitecture using AXI on FPGA. The caches carry around tags as sort of an implicit but inherent, atomically integrated part of the data. But where does that come from? It comes from these tags stored in DRAM in this design using a tag controller and separate tag table. Let me tell you just briefly about the software side of the house. So we have this set of properties, we have this microarchitecture, they push up and support the software design when the software uses it. And so how can software use it to get these properties? So the two key use cases I mentioned were this efficient fine-grained memory protection and then also the scalable compartmentalization. So our objective was good, or ideally extremely good, source level compatibility. In a recent study, we required 0.026% lines of code change to a 6 million line code base. I mean, probably maybe a slight underestimate because of the limits of dynamic testing, but I think that's a pretty good rate. I mean, earlier papers we published sort of 1% to 2% lines of code change. We have improved our results dramatically, in part by improving our use of capabilities in C and our adaptation to the C language as we kind of discovered the rough edges. I think also because our early studies were really focused on low-level system software where there is more disruption because they have to know more about capabilities. Whereas in the high-level code, we were looking at many fewer changes to run with memory safety. So various kinds of memory safety, temporal memory safety, I think is a challenging thing. In Cherry or in capability systems and architecture, it's kind of interesting. So like C and C++, the use after free problem, roughly speaking, maps into the revocation problem. And in capability systems, revocation is hard. Well, it's easy if you're willing to have centralized data structures and lots of synchronous checks. But today's microarchitectures are not very centralized and they're definitely not very synchronous. And so we chose not to make revocation efficient in Cherry. We instead allow capabilities to flow all over the place and not require continuous checks as to whether the things have been revoked. Therefore, we choose to take a penalty on temporal memory safety handling in order to make spatial safety much more efficient. And we pay some costs for that, and therefore we have some limitations. So for example, today we currently apply heap or temporal memory safety to heap allocations, but not stack allocations. So we have limitations to what we can do there. On the whole, what kind of overheads? Usually the hand wave number is 2%. For many workloads, it's actually 0%. But if you're working with pointer dense language runtimes that have lots of pointers in the dynamic access patterns, and then you look at the slide I showed you earlier where I doubled the size of the pointer. Well, when people went from 32-bit to 64-bit, they really noticed that for these pointer dense workloads. And you notice actually when you look inside language runtimes, they often don't use 64-bit pointers even inside a 64-bit address space. They'll use 32-bit pointers or compressed 37 or 39-bit pointers. So there are some challenges there, and there are the same trade-offs as well, actually maybe slightly more complicated trade-offs. I mean, you can still use smaller pointer sizes with Cherry, but you're not getting the protections for those pointers. And so there's a security trade-off that's introduced if you want to use those optimizations. The compartmentalization work, I use this phrase a lot, software operational models. It's ways to use the architecture to achieve some abstract goals. So we can implement objects, we can implement processes, various other things. But there are lots of trade-offs, and we improve some things and we hurt other things. We keep the MMU around, and so we can often choose which to use for some purpose. And that's a helpful thing to be able to do because there are things MMUs are very good at. I mean, once you've decided to take their cost. For example, the revocation problem might sometimes be mapped into an MMU-based invalidation problem. So we could use the existing table, although we tend not to. Whereas there was a performance overhead argument for memory safety. It's a really small overhead, we promise. For compartmentalization, it's a performance win argument. In our early benchmarks on FPGA, we see a 90% reduction in small message size message passing between compartments compared to using processes. And that is a big deal because when we add compartmentalization to software, it's often across API boundaries that carry small amounts of data on individual calls or references to data. And potentially we make that much more efficient. Actually, a lot of these questions about performance and efficiency, the answers are going to be very clear very soon once Morello is available and we can actually go run it on the real thing. There are some other potential use cases around language runtime reinforcement, communication between high-level languages with a sort of a safer interlanguage interoperation substrate. Those are topics we've not really explored in research. We would love to explore them or encourage other people who maybe know more about language runtimes than we do to explore those kinds of topics. A few sort of high-level notes on C and C++ memory protection. So, I mean, the basic concept here is that we're going to implement our language-level pointers, the explicit ones, the ones the programmer sees, obviously all those, but actually also all the implied pointers, the control flow pointers, the stack pointers, the PLTs, the GOTs. We're going to reinforce them and we're going to protect them. The goal there is provide integrity for them, provide spatial safety. It's kind of interesting to ask what that looks like under the hood in your language, right? I mean, these implied pointers exist and aren't seen by programmers, and yet they're the tools attackers are using. So they need the same kinds of protections we've been talking about. So this changes C and C++ a bit. Right? All pointers have to have a well-defined single provenance. That word single turns out to be quite important. So we do narrow some of the things you can express. We have some requirements about alignment and pointer size. You have to be a little bit more careful about mixing up integers and pointers because your integers aren't capabilities on the whole in the architectural view. You have to carry the tags around. There are these minor changes. They turn out to be pretty minor for most things. I'll show you some numbers. We have a programmer's guide which talks about the kinds of changes. It's not a short document. I fear it will only get longer, but hopefully maybe a reassuring document. So let's think a bit more about these kinds of protections. So capabilities are going to be, they're inherent to the architecture, how we refer to data, but they're refined along the way. Their bounds are restricted or they become opaque or whatever it might be by trusted computing bases. Not necessarily globally trusted, but certainly trusted by their consumers. So the kernel, the runtime linker, they're all things today that calculate and manufacture pointers and perform allocations, whatever allocation is. And so those are the things we're going to represent using capabilities. They're going to control the capabilities. We have these different kinds of protection that come up, therefore, pretty explicitly out of what the architecture provides. It's a very natural mapping, I think, for all of these, actually. We go back and forth on whether temporal safety, the mapping is natural, but I guess you have to wonder, what does natural mean? Virtual memory mapped into an MMU is obviously incredibly natural, but incredibly hard work for a kernel VM system. And temporal safety is a bit comparable. The spatial safety is simply, over compiling to capabilities in some sense. And we do this automatically. So 2 levels. So there are these language level pointers. These are the programming language visible things, pointers to memory mappings, pointers to thread local variables, all these things. We try and protect them. And then below the language, we have these implementation concepts that are generated by the compiler or the linker. And to do this, we kind of had to do 2 things, right? We had to reverse engineer the structure of software. I discovered I really didn't know how computers worked. Basically, any level of execution is very educational. But then also we're changing the behavior. So the experiment is, what is the impact on all these things? Does minimizing privilege cause problems? You have bounds or provenance validity or this monotonicity property. There's the potential for interruption or interference with these things. And sometimes we do. Memory allocators do have to change modestly as a result of this work. So if we have temporal safety and spatial safety at the language level, why do we want to also protect the things under the hood? Well, there's a few different reasons why this might be the case. I mean, the first is the limitations of what we've been able to do. Yes, we prevent buffer overflows. Yes, use after free can be precluded, in the structural design of the software. But I already mentioned, we found that we can do this use after free protection for heap stuff, but we can't do it for stack stuff. There's also places in the language itself that, introduce concepts of type confusion that attackers take advantage of. If you have a union that uses the same storage for an integer and a control flow pointer, there is the opportunity for something to go wrong in a way that we can't say you're just not allowed to do that. At least we've chosen not to say that you're not allowed to do that. Therefore, the reinforcement that exists under the hood is quite important. It also helps us potentially with things like compiler bugs and when we're containing malicious code generated by someone else. We need to constrain its execution and protect our own data structures. So I think we consider this very important, although we make, I think, weaker claims. I think we understand why having spatial safety helps security. I don't think we really understand in a fundamental sense why all the techniques that exist around control flow and so on help security. They seem to limit attackers, but that's not quite the same thing. So something to think about. Again, we do the wait for PowerPoint this morning. So how should you think about this? What you should think about is that your program is tied together, woven together using integer pointers today. And all we're really doing in Cherry is we're saying for memory safety, we're substituting capabilities for addresses all over the place. We're not even necessarily introducing many more of them. Sometimes we have to for utility reasons to express ideas. But on the whole, we're really just taking the existing execution substrate and structure of your program and reinforcing it. metaphor is a terrible thing. Here's a terrible metaphor. So, what was the impact of the invention of reinforced concrete? Well, I mean, it allowed you to build the buildings you have much better, much better structural properties. Also allows you to build new kinds of buildings. And Cherry is a bit like that. Cherry takes our existing designs. It tells us how, we recompile them. Let's see, the metaphor breaks down. You can start to pick up protection properties simply by making the substrate stronger. But it also tells us that we can build new kinds of things. And the new kinds of things we have in mind are things like software compartmentalization. Situation with PowerPoint is becoming slightly dire. I think what I'm going to do is I'm going to stop the sharing, restart PowerPoint, and try again. We'll just hope for the best. Yeah, that seems better. These capabilities have to be managed, so our software TCBs, as I mentioned, are busy refining these protections throughout. And then the hardware is taking these policies, if you will, that have come out of software design, and it's just continuously enforcing them as the program runs. So talk about software compartmentalization. First question, what is software compartmentalization? So software compartmentalization is the fine-grained decomposition of some software system, some large software system, into an isolated set of modules to constrain the impact of faults or attacks. So it's, if you will, software sandboxing. Software sandboxing, though, is a very limited example of what we want to do. Software sandboxing itself is very limited on current hardware. If you have the Chrome web browser, at some point you're starting up tabs and they run their own processes, and at some point, Chrome decides, well, if I'm going to create any more processes, we're really going to run out of oomph. Right, the system is just not going to handle anymore. We're going to start combining your tabs in the same processes. One of the things that's limited site isolation, the assignment of sandboxes to individual remote websites has been the scalability of MMU-based protection architectures. So in Cherry, our goal is to have different scalability properties to make some things more efficient in return, perhaps for other things becoming less efficient, and then we can blend it with our MMU-based design. PowerPoint experience is very disappointing today. So I mentioned privilege minimization. There's actually another aspect to compartmentalization, and that is when you have performed a successful attack, not only are your privileges minimized, but also we're limiting further attack surfaces. You have access to fewer interfaces, and ideally interfaces are better protected. So one way to think about compartmentalization is we construct a set of compartments that's executing code in lots of little boxes, but they're linked into a graph, interconnected components. And the attacker's goal, basically, once you find an exploitable vulnerability, or you have a Trojan horse, or whatever it might be, in one of these components, you're working your way across the graph to get to a node that has the privilege you're actually looking for, the privilege to access a file or a key or control of the system as a whole. And we can model our current software systems this way. When we look at iOS, for example, many software compartments in software sandboxes using the MMU. As an attacker, we have an exploit chain to first, compromise some web browser component, and we have to escape from sandboxing to compromise the kernel. I mean, that's very much the same thinking, but the goal in our work is to take that much further. It's to allow us to have sandboxes for things you couldn't have had sandboxes before because you couldn't afford it. So for example, the processing of every individual image, media codecs and video processing, image processing are, for sad reasons, incredibly error prone right now. And memory protection helps with that, but it's not sufficient. There's also an aspect of compartmentalization when you've removed these vulnerabilities or you've rendered them impotent, if you will, about denial of service, which is, your image rendering library crashes, it takes out your tab. I would really like to be able to contain that to a much smaller area. So on the left-hand side, I have actually a mechanically extracted sketch of a set of compartments in a modified FreeRTOS operating system that we've designed, in which we take advantage of linker information and compile time information to isolate various components. They have explicit and implicit relationships. There's a TCB at the bottom that they're using for domain switching, for memory allocation, and so on. And the goal there is indeed, you have some vulnerability in your TCP stack, and you can't immediately have full system privilege, which in an embedded system you normally would. But not just that, you have to sort of go from component to component as you make your way towards it. Of course, there is a TCB. TCB is your hardware. TCB is, a small microkernel operating system underneath it. You would obviously try to go to attack those, and that is where we need these other things like formal designs, and we need memory protection and so on. So what's the challenge? Well, we can decompose software in many ways. There's a space of the ways, of course, and these space trades off, disruption to your program, the performance properties, the security properties, and so on. We argue in the abstract, principle of least privilege says, make these compartments smaller, you better approximate the principle of least privilege. But unfortunately, in our MMU-based designs, this doesn't scale. There's poor scalability, poor granularity, poor context switch times, and to be honest, a terrible programming model. The multi-address space model is the painful thing. So we can then look to Cherry and we can say, okay, well, if you can only access resources using these capabilities, you can't manufacture them, you can't read outside of them. Monotonicity says you can't take a write and expand it to cover things it's not supposed to expand. We can take these graphs of capabilities and we can set them up in ways that give us, if you will, protection domains, right? Isolated compartments. So we can give you, through your program linkage, the ability to access your own private data, maybe some shared heap or shared code. And we can create other domains that have some overlap. And now they have quite efficient shared memory communication. In fact, even sharing TLB entries. And we can also switch between them as register file switches because our capabilities are held in register files and describe our accesses. We don't have to invalidate tables and so on. So there's the potential then for quite high performance behaviors. So what are the opportunities? Well, we can have more compartments. We can have more frequent domain transitions. It's the second aspect here we've really focus a lot on as how to get that context switch time down to not quite function call, but within an order of magnitude or maybe a linear factor of function call, rather than many orders of magnitude, and then very fast shared memory between them. And there are many potential use cases. We can scale up the sandboxes we have in existing applications. We can craft new kinds of software and new kinds of applications. But I think, the argument I was making around memory protection is, you can recompile things and it works pretty well. Software refactoring is required to get to compartmentalization. And we think there's a hard and quite interesting set of research problems there. But I think it's also the fact that people are using compartmentalization today and struggling with the performance of the architecture is really telling. I think if we can make it easier, we can make it faster, then maybe we can also work around making it easier to do these restructurings. It's an architecture, it can do different things. You can use the MMU in many different ways, virtual machines and processes and microkernels, all the stuff. I mean, Cherry is the same in that sense. You can use it for different things. We have lots of questions to answer. What are compartments? How does software represent them? Are they function calls or messages? How does debugging work? These are all great questions. And so we have to come up with new software operational models that describe the kinds of behaviors. And the trade-offs are complicated, right? You have to gain experience in how it works. And that's what we're doing right now. We look to different inspirations. The Unix process model is a good inspiration. I mean, people understand how to use it, how to debug it. We've answered these operational questions, which is great. So we can make process context switching in IPC really fast, but it's not the end of the story. I think we're also interested in other models. And in particular, one that we're interested in is the sandboxing of libraries. What is the consequence of a crashing library? We understand for a process, but for a library, we need to have some new ideas. And so I think some iteration is required to decide how we want these things to behave. So these are possible using Cherry, and this will exist in Morello. And we've also done quite a bit of prototyping. Just the last few minutes then, talking about Cherry and transition and a couple of thoughts on evaluation. So we have two DARPA-supported Cherry adaptations. We have this RISC-V adaptation and our ARM adaptation. The ARM collaboration started in 2014. It was something we started talking publicly around, I think about 2019 when ARM announced Morello. It is a multi-core implementation. It's done it in collaboration. I mean, they have specified the architecture and we work closely with them to understand that, to test it, to prove things about it, to validate it using software. We have our open source RISC-V implementation. The RISC-V implementation is what we use for research. I think it's also, quite easily the possibility of technology transition there, but it's what we share to have reproducible research and, and help others set up. I mean, you can actually run it in Amazon AWS F1 if you want to. You can spin up Cherry processes and experiment with the software we have. And for each of them, we have a full elaboration of the hardware software stack. We have all aspects of the architecture enhanced to use Cherry features. We have the formal proofs, we have the compiler, we have the operating system, and so on. Again, we'll start waiting on PowerPoint. We've restarted PowerPoint, so I think there's no hope for us other than to just occasionally fall out of the presentation and then go back into it again. So we've collaborated since 2014, and we've been doing a bunch of interesting things. On the one hand, I told you like quite blithely, without any detail, it's an abstract protection model, but Cherry had to become architecture neutral as part of this transition work. It seemed like a good idea, but it was not guaranteed that when we tried it, that would work out. The answer is, it turns out it does. And it works for many different concrete architectures, which is very exciting. So we can try it out in all these different contexts. We had to really improve our approach to microarchitecture as well. We had to understand how to reduce critical paths, how to deal with extra memory accesses that, as academic, we didn't understand some of the optimization goals and points that were important. So in particular, in the transition from 32-bit to 64-bit, there was a big focus on reducing dynamic memory accesses because the pointer size growth was influencing cache access. So we knew about the cache split, we knew about the performance impact, but we didn't realize that something that really important to vendors was the increased energy use from DRAM accesses. Ideas also had to apply to software. I mean, is it possible to have a portable Cherry software stack where, just like virtual memory, you can hide it, the details in a few places? Yes, is the answer. I mean, the places are a bit different, the things like your runtime linker and so on, but they're all places where you had to have architecture specificity anyway. Which was quite encouraging and surprising. So compiler backend, for example, needs to know about Cherry, but the compiler front end doesn't need to know about Cherry for ARM or Cherry for MIPS or Cherry for RISC-V. It just needs to know about Cherry. And then we had to expand our software corpus to try and produce better and larger demonstrations of scalability for ARM and for its customers. We extended the modeling and proof work from I would say RISC-V is a toy. RISC-V is small, right? MIPS is small. ARM v8a is very large. And we had to solve a lot of practical problems and build evidence and templates for use to allow these ideas to be transitioned. So where does Morello come from? Morello is a research project. It is part of a large-scale research program in the UK, funded in part by the UK government, £70 million. I don't know what it is these days post-Brexit. It's feeling like maybe uncomfortably less than it used to be, but maybe it's $100 million. Another 117 million from industrial matches, the likes of Google and Amazon and Microsoft, who committed to invest substantially, and ARM has certainly invested substantially to create the architecture, the ISA, and then produce a board and design, and then do things with it. And the goal there is to address a supply chain gap, if you will. So it turns out deploying disruptive new architecture is really hard. I mean, deployment of GPUs, it literally took decades to get to wide-scale use, right? The reason is that you need software demand. If we really want this thing, and you need the hardware people to satisfy that demand, well, I mean, the hardware people can look at the design and say, yes, I think we could build this, but where is the software demand? Software people say, this sounds great, but I don't have any hardware and I don't have any in 2 years. I'm not going to invest in building software prototypes on top of it. So in order to bridge that gap, we actually need a piece of hardware that can be used by software people to decide, does this do what I want? We hope that it does. But that's the goal of the program. A significant industrial and academic support coming out of UK funders on reuse the existing Neoverse N1 baseline processor design, which they extended with Cherry, and then went through a tight collaboration to decide, and it's an ongoing collaboration, which features need to be in Morello, which features need to be in a product, what are useful and desirable. And science was allowed. So the design of the chip and the board includes multiple design points. I mean, this affects the efficiency of the microarchitecture and clocking, but it allows us to run experiments we couldn't otherwise run, such as there are 2 different ways to implement tags in the hardware. So emulation models come out, board delivery, the boards will start turning up late this year, primarily for very early adopters, that's us, but next year available more broadly to academia and industry. So I just mentioned, the specification, Cherry RISC-V specification, maybe 100 pages or something, maybe 70 pages. Specification for Morello, over 2,000 pages, reworks aspects of the instruction set, is a serious engineering effort. Includes our most recent research around temporal memory safety. So it's really synchronized to about 2020, 2019 design of Cherry, which is very exciting. So some fresh stuff in there we actually hadn't implemented in our own microarchitecture. It is what ARM calls a superset design. A superset design is one that contains features that are not just complementary, but maybe feel a bit redundant. When there are 2 or 3 different ways to do things, ARM would generally prefer to have one of them in the production architecture. But in this case, they've included more than one of them so that we can run these experiments and understand, what is the best way to spell the main transition, for example. I should, of course, mention the constraint. this is not a commercial product. This is a prototype, and there's an architecture embedded in it, instructions of architecture. ARM does not guarantee an eventual product will run the binaries that run on this board. In fact, I think they pretty much guarantee that they won't run the binaries that exist on this board, but hopefully they will carry forward all the successful aspects of the architecture. And I think we'll probably find that software stacks really recompile and run, as opposed to there being substantial disruption. I think OS will probably have to know the details, but ideally not application level code. The completely obligatory block design. I mean, there are 4 cores. There's a GPU. There's I/O devices of various sorts. This could be a desktop, it can be a server, it can be a synthetic mobile device. I mean, ARM is providing an adaptation of Android to run on it. I'm slightly late because of our PowerPoint problem. Maybe I'll just run, if our hosts don't mind, a couple more minutes just to mention a little bit about software and some of the results there. I'll take silence as tacit approval. Okay.
Please do.
Yeah, I'll try not to run too long. So we ported over our software stack. I've not said much about software, so I'll show you a slide in a moment. But basically, we wanted to do a couple of things. We want to validate the Morello architecture. Was it functional? Was it sufficient for our purposes? And then evaluate the implementation. We aren't there yet, right? We don't have the chips in our hands, although we are able to run it on FPGA. Performance, energies, and so on. These are the key viability questions, because the goal is to do some things much more efficiently with new just-in software, other things faster than we can do today, enabling new software architectures. Those claims have to be true for us to deploy this. And so I think, a very exciting moment, I think. What is going on with PowerPoint today? I'm sort of afraid to ask. Another thing I keep talking about, we have to change software semantics, new APIs, what is an object? I mean, we have to provide, I think, reference semantics, among other things, reference compiler and OS designs that really demonstrate how to use the ideas. They probably aren't the exact way we'll eventually use them, assuming we're successful in decades' time. I mean, if you look at the way people use virtual memory today, it doesn't, yes, you can steal the design principles that came out in 1990s and 1980s MMU designs, but the spelling is really different in how we use them in operating systems and languages. I think no reason to think it will be different, but on the other hand, you have to provide a successful and useful operational model to start with. Otherwise, people won't be able to use it. If you provide a board that can't run anything, that's of limited utility. And to act as a template for use, to go to industrial partners and say, okay, here's how you might use it in your product. It's quite important. And as a research project, so 11 UK-funded research projects have recently started up. There are projects in the US funded by DARPA using Cherry and so on. So I think there's a lot of exciting opportunities, but it's very research-facing right now. So we took an open source software stack, to be brief, and made it run with Cherry. Sometimes the changes were substantial. We have heavily modified compiler backends. Other times the changes are modest. We have modest changes to the FreeBSD kernel, to bits of user space. And other times, barely any change at all. I'll talk about that in one slide. There are areas of research that are interesting. RISC-V doesn't support virtualization, at least not maturely now, and it certainly didn't when we were building the Cherry RISC-V architecture. So there are some things that are really available only in Morello, such as integration with hypervisor features. So our software stack is catching up. We now have, as of a few weeks ago, booting guest operating systems using Cherry. The goal was to have a rich stack. I've mentioned ARM is also bringing over Android and Linux. I think those will be extremely useful. I think the glide path is long, right, to get to a fully functional operating system, which has temporal memory safety and processes implemented using Cherry features and virtual machines. So I think right now, to experiment with these ideas, you'll need to work with the stack that we have. And on top of that, we have an off-the-shelf open source application suite. We have things from KDE and web browser, Python programming language, and you can run unrecompiled legacy binaries, but we encourage you to use the exciting memory safe ones, or maybe the too exciting compartmentalization enabled ones. I talked a bit about CherryBSD, or at least about OS design as we went through. The quick version is that everything is memory safe. In some places you have temporal memory safety and user space. In other places you don't. We don't yet know how to do that in the OS kernel itself. And a bunch of exciting design questions, basically come out through working with the software corpus. How do things like monotonicity and provenance validity affect software in practice? I'll just conclude by mentioning a 3-month pilot study we recently concluded. So here we took about 6 million lines of code from the open source desktop corpus. We worked with X11 run and KDE because of the hardware run and the emulation environment. We used Qt, we used KDE. We implemented referential spatial memory protection for all of these. We whiteboarded a set of compartmentalization, and we evaluated. We can't evaluate performance in emulation, but we will do that once we have the board available. We'll publish in mid-October. We'll publish a report tomorrow, I hope, that contains all the details. But we evaluated retrospectively vulnerabilities in the software stack. I think it's pictures in slides. The obligatory picture, KDE desktop, everything you see here runs with full C and C++ memory safety, which is quite an exciting thing to say. It says 6 million lines of code, 3 compartmentalization case studies. Depending on what we look in the stack, between memory protection and compartmentalization, we find mitigation rates that vary between about 40% of published vulnerabilities are fully mitigated in KDE, up to 100% of vulnerabilities in supporting libraries like JPEG libraries and ping processing and XML processing and so on. These are whiteboard analyses. There's a very nice report out of Microsoft Security Response Center, MSRC, late last year, early this year, and a Black Hat talk this year talking about vulnerability mitigation in the Microsoft stack, where they estimate 70% of critical vulnerabilities are mitigated by Cherry. That is the kind of number you need to deploy a very disruptive technology. There are lots of limitations. I'm afraid I don't have time to talk about them now, but they'll be in the report in painful detail. So, if you want to install our stack, it's open source. You download one tool, it builds emulators. It can download ARMS emulators, build our own, builds compilers, operating systems, that works. I'll encourage you to take a look at the slides on our website to find that information. So having run slightly long because of our PowerPoint difficulties, I'll wrap up. If PowerPoint will does it even get to the last slide, just amazing. But I'm just saying there's a lot of research to do. I mean, Morello is really exciting. It's a transition path, but it's also a research platform. And we have lots of unanswered questions about how you do language runtimes and debuggers and tracing, things that interact with the structure of your program need to interact with the security model. So a lot of great topics that people are interested. I'll wrap up. I apologize for running a bit long. Cherry is new architecture, it's new hardware, it's new software, it's exciting. It's research. It tries to balance all the inevitable tensions, compatibility, performance, effectiveness, but do something different than what we have. It's not free. It does require new hardware deployment. It does require change to your software stack, but I think it is a really interesting set of ideas, and it has surprising legs so far. I mean, the goal when we had initial DARPA funding in 2010 was, roughly speaking, blue sky research. It was, if you can disrupt everything, what would you do to improve security? I guess this is our take on what you would do. So I guess time permitting, I'll take questions. Time might not permit. I'll refer you to our technical reports on our website. We have a Slack, by the way, cherry-cpu.slack.com. You need an invitation to join, but you can find all the details on our website. And I'm happy to field questions there if that's a better venue. Thank you very much.
Yes, thank you, Robert. We do have some questions actually in the chat, so we will take a couple of minutes still of your time, if that's okay. So one of the questions is, did you investigate the interaction between Cherry and modern safe languages such as Rust or Swift? And do these languages lessen the need for hardware-assisted safety? Would it be easier to use them and then compile to Cherry?
Yeah, these are great questions. I mean, the first thing I should admit is, I don't think we know the answers to all these questions. We have done some work with high-level languages. We had a paper a few years ago at ASPLOS looking at how Cherry could complement JVM design. So, Java has a language security model, it has a sandboxing model. And what we used Cherry to do was encapsulate J and I code. So native C and C++ code, you were going to link into your Java application anyway. If you look at Java applications, some contain a lot of native code, some are mostly native code. So we wanted to impose the Java memory safety model on the native code and the sandboxing model, and we did that successfully. This was on MIPS on a pretty small core using a small JVM. There's now an effort in flight at the University of Manchester to take OpenJDK and do very similar work, target the memory safe substrate with its JIT, apply security models. So I think there's an exciting opportunity there. And I guess if you take a step back from what I've said, well, keep your type safe managed language, but where you have interesting things going on with native code and other languages, there's the opportunity to improve it. If you have a language like Rust, I mean, Rust is great. Rust also has limitations. So, is there a way we can use Cherry to help with the safety of unsafe pieces of code in Rust? I mean, there is substantial unsafe code there around memory access and synchronization and I/O and so on. It's possible Cherry can help with that. I don't think we know the answer to that question. Another thing that people do is that they link high-level languages. If you look at composite applications, monolithic applications in OS parlance would be, OpenOffice or web browsers. They often have many language runtimes and many languages. Can they interact more safely using Cherry? Maybe. Probably a good guess that they do, but whether it's a good idea, I think is an exercise that it has to be explored empirically. We won't know until we try it. There's a lot of interest in making Rust compile to Cherry. One of the reasons you might do it is to improve the cost of dynamic checks that your language implies. I mean, Cherry was not designed to accelerate dynamic language performance, but it does include architecturally assisted downs checks and things like that, and tools for temporal safety that could improve garbage collection performance. There's a project at Glasgow looking at whether you can use the temporal memory safety features we designed for revocation, for garbage collection in managed languages. So I think there's some great opportunities, but I don't think we really know the answers to some of those questions yet. And as I said at the beginning, in the long term, please use your formally verified type-safe language, maybe managed language. If you have that, maybe you don't need to compile to Cherry. And on architectures that support Cherry and legacy code, you can compile through to your non-capability instructions. A question that's not well answered by those languages, but is by Java, is when you have to interact with code from an untrustworthy source, how do you contain it and interact with it safely? So a Rust OS kernel is a great idea, but when you're hosting even Rust applications compiled by someone else in your processes or your tasks or whatever your container is, Cherry may be a really good way to do that. Hopefully we'll find out in the coming decades. And I think Morello is a really good place to run those experiments because it's much larger scale than the FPGAs we've worked on so far.
Thank you. There was another question. How does Cherry relate to current new developments like the ARM version 8.5 memory tagging extension, or ARM Apple pointer authentication, or even fully software solutions like ASAN?
Yeah, I mean, these ideas all relate to each other, but I think they're all quite different and they offer different things. There are trade-offs. So maybe PAC, which is the pointer authentication extension first. I mean, we provide memory safety. PAC provides hash-based, key to hash-based integrity for pointers, and those are very different things, right? I mean, PAC is intended on the whole to mitigate exploit techniques, so sort of a fairly important but narrow set of techniques, whereas we intend to close vulnerabilities. We intend to prevent the things that allow you to corrupt those pointers in the first place. Hash-based techniques are based on the secrecy of a key. The key is a bounded size. The attacker has the ability to try and guess it. The hashes are really small. You have a few bits at the top of your pointer that are available. They're subject to collision. They're subject to brute forcing. They're subject to information leaks. If you leak a pointer for PAC, or I mean, for that matter, ARM MTE, the attacker has the information necessary to re-inject it. Cherry doesn't allow re-injection. So we provide deterministic, secret-free protection in situations where a lot of those techniques are mitigation techniques that may help you against one-shot attacks, but are, in the context of, a full system. I mean, if you have like Apache or Nginx that use fork, the Android runtime, they reuse the same process address space layout over and over again. So protections that protect the integrity of your pointers, you steal one from one process that crashes, that leaks, or whatever, and you can now re-inject it into other processes. So these kinds of properties are really important. PAC is much less disruptive, I think, to the microarchitecture than Cherry. It doesn't change the architectural model, it doesn't change your pointer size. So Cherry is more disruptive. Most of those techniques are, about some extent memory safety. None of them talk about compartmentalization and granularity. So there's also a very different set of objectives. I think MTE is really interesting. This is the tagging extension. Those ideas, I think, originate, perhaps like in some 1980s CMU research, but end up in, Oracle Spark hardware design. They've now made their way into ARMS design, courtesy, the LLVM analyzer team at Google, who do ASAN as well. So you could view it as accelerated ASAN. They've done amazing work at discovering vulnerability. And the argument they make is, find vulnerabilities and you don't have to patch them in the field if you can find them in the development cycle. And they've been incredibly influential at finding large numbers of use after free bugs. ASAN is very powerful, but very slow. I mean, half the performance of your application on a good day. MTE is designed to accelerate that. I think MTE is a great debugging tool. I'm not yet convinced by it as a security tool. A fascinating research question, though, is could you combine ideas from MTE with ideas from Cherry to improve our revocation performance? And it's a really interesting idea. We have sketched some things in our ISA spec from a couple of years ago and said, you could do this thing, but we have no evaluation. And we're really interested to see how that plays out. But an unanswered question about MTE is what its actual performance is, because hardware hasn't shipped yet. And I don't think anyone has published performance numbers for MTE.
Another question was posted. How does Cherry fit with something like kernel level memory protection, such as that is available with SEL4?
I think I don't quite understand the question. I'll say some words that resemble the question, and if that's not sufficient, maybe the questioner can drop me an email or ask again. So I mean, SEL4 is a verified microkernel. Do you need Cherry if you have a verified microkernel? I mean, we think so. We don't think you need Cherry memory protection inside your microkernel because it's proven to be, memory safe C, right? It's proven not to overflow buffers. It's proven not to use memory after it's read. I mean, SEL4 is stylized C as well that prevents even expressing some of these kinds of vulnerabilities in return for reduced expressibility. So I don't think I wouldn't mind if someone compiled SEL4 using Cherry, but I don't see a benefit to the internal protection of the microkernel. I think the interesting question is, can you use Cherry's protection features and high performance IPC features through some modest redesign of SEL4 to host Cherry-enabled guest operating systems or user tasks that are not themselves verified, or are verified, but you don't trust where the binaries came from? Can you use it to have many more compartments on top of SEL4 and have compartmentalized software over SEL4 be much more efficient with many more compartments? I suspect the answer is yes. A great project would be to bring SEL4 to Morello and experiment with these ideas. There's also a longer term question, which is, could you recraft SEL4 so its ideas about capabilities are somehow aligned with Cherry's capabilities? Cherry encourages design patterns that aren't possible with MMU, such as function call semantics or domain switching with shared memory. Right now, SEL4 is very MMU focused, right? It's about page mappings and virtual memory oriented IPC. We could redesign SEL4 to support Cherry really well. So we have a technical report coming out in a few weeks. One of my PhD students has done a clean slate operating system microkernel based on Cherry to kind of just ask the question, like, what happens if you go a bit crazy? What happens if you don't start with a Unix operating system and just like add Cherry stuff to it? Instead, what happens if you design an OS for Cherry? A very long-term research question, but like a really fun one is, okay, what if we did that to SEL4? What if we lifted the ideas out of this Cherry OS or other ideas and blended them? You get a new kind of operating system, and we don't understand what that would look like. In general, though, just like if you have the words Cherry kernel memory protection, we expect OS kernels should use Cherry for the same reason your application software should use Cherry. They should be compartmentalized. They should be memory safe. You should take those things for granted. In our Cherry BC reference OS, the OS kernel was compiled with spatial safety and referential safety, but not temporal safety, because memory is funny in kernels. We don't really yet understand how its memory allocators and virtual memory interact with our temporal safety ideas. It's a research project we're starting to pursue, and we need to look at it in more detail. But I hope the answer is going to be a sensible one, just like it was for user space.
Okay, I think we are going to close the questions here in the live session. If anybody still has questions, maybe you can hang out a little bit, Robert,
yes,
and go to the Zulip chat. And then thank you very much for your talk.
And thank you very much for your invitation. It was great talking to people.
Thank you. That's great.
And